Again, my name is Dina Zini, and my talk's about the optimization of metasurfaces for computational imaging. I'm a PhD student in the Applied Physics Department, and I'm advised by Todd Zickler and Federico Cabasso. So before I begin, I just want to talk briefly about the design of a conventional imaging system. And when I say conventional camera, you probably think of one of these three things. It might be like an iPhone, a Sony DSLR camera, or possibly, but not likely, a vintage Polaroid instant camera. But it actually doesn't matter which one comes to mind because the design paradigm of all these cameras are largely the same. Their operations based on the idea that a single point in your scene should project its light to a single point in your photosensor plane, like with ray tracing. And consequently, the captured measurements are what you might call undistorted projections of a scene. And they're very close to the final image that you show a user without post-processing. And if you actually look through the history of cameras, it's almost always been this way, dating back to pinhole cameras in 500 BC. But in this talk, as we transition to computational imaging, it's useful to note that the design of computational imaging systems fundamentally deviate from this idea. So more formally, this description about the behavior of cameras encapsulates a quantity known as the point square function. It's essentially the impulse response of an imaging system. And it's computed by considering a single point source at the object plane and then measuring the intensity that it projects to an image plane. And the centuries-long pursuit of an ideal lens is really just to have a point square function that's a delta function for all illumination scenarios. But there's a lot of ways that you can deviate from this, and they're called aberrations. And those with nice mathematical forms, or those that have been really common historically, have been given names like defocus, astigmatism, and spherical aberration, and things like that. Now, underlying this talk is actually the basic idea that I'll briefly try to convince you of, otherwise, you might just have to take my word for it. It's that moving away from ideal focusing to these other structured point spread functions can actually enable better vision systems and cameras, specifically when we have digital post-processing available to us. And the heart of this talk is a discussion about how we actually go about engineering these point spread functions for computational imaging using a new type of optic called the metasurface. Now, to give you some concrete motivation, nature actually knows very well this idea of computational imaging and utilizing point spread functions. And a famous example is the way that the jumping spider perceives distances when looking at a scene. And it's actually based on optical defocus. So the main eye of a jumping spider is a point spread function that's depth dependent, meaning that it sees its prey with a different amount of blurriness depending on distance. And if it can figure out just how blurry an object appears, then it uses that information to decide how far to jump. The actual vision system is a little bit more interesting than that because they have eyes designed to capture two blurry images at once and actually computes the differences of the two as a type of triangulation. But the key detail is that they compute depth maps for a computational cost lower than anything human has ever made. This feat of efficiency emerges because they have co-designed this post-processing algorithm alongside this non-ideal lens. Now, speaking of imaging, I first want to talk a little bit about what makes up a scene that we look at from a physics perspective, because it's a lot more than just a 2D RGB image. First, the scene has this dimension of depth, which everyone's already familiar with, but it can also be characterized by this tensor, which we might call the spectral radiance, and underlies the color that we perceive, because color is a perceptual phenomenon. Now, the spectral radiance describes the fact that white light is a superposition of many independent waves, each with a different wavelength, as can be seen when using a prism. And when white light is incident on a surface, each of these waves will reflect with a percentage that depends on what the surface was. So if we sequentially place the narrowband spectral filter in front of our lens, we could measure the intensity of the scene at each narrow wavelength channel one by one, and this would give us the full spectral radiance cube. And this is a type of data that we'd like to have access to beyond just the RGB of the scene. And lastly, I want to talk a little bit about polarization. So each light wave at each wavelength also has its own polarization state. So it's defined as the orientation of the oscillating wave. And you might remember learning about Brewster's angles in physics, which basically said that the scattering or reflection of light depends on whether the polarization is at an angle normal to the page versus along the page. And so that ends up being important for imaging. Now, with a conventional camera and a glass lens, you're generally not sensitive to polarization of light. You can't distinguish these different orientations. But again, this data about the scene is really useful to have. So similarly, we could put a linear polarizer in front of the lens and we could rotate it and take multiple images, and this would give us the polarization composition of our scene. But instead, we can actually get all three features of the scene at once in principle, by using computational imaging and encoding these properties with a specialized lens. And basically what we'd want is a feature-dependent point spread function, very similar to the depth-dependent point spread function of the jumping spider. Now, computational imaging and optimization can be applied to answer this question of how do we recover the full information of the scene, or at least best encode the quantities in the measurements that we take. And the measurement for doing this is the motivation for doing this is that we require more than just a 2D map of the scene, the so-called ideal image, in order to interact with the world. We really need a collection of statistics like material identification, segmentation, and depth. And these are actually all things that we can determine more accurately if we had the spectral radiance and the polarization data. So I just want to talk a little bit about the design pipeline of how cameras are made. So suppose you have a scene that's imaged on a camera using a fixed lens. Now, generally, this lens is made by an optical engineer without any sort of special consideration to the downstream task. So by default, it's just approximately an ideal focusing lens, like I showed you at the start. And given the measurement, it's then in the domain of computer vision researchers to train deep neural networks or to drive simpler algorithms for things like predicting spectra, depth, or segmentation masks. And they have to learn to do these things without using any sort of special optical cues in the image. And unfortunately, these are severely ill-posed problems, so they fundamentally cannot be solved exactly. But a better way to do this, to get better performance and confidence, would be by removing the separation of optics and computer vision. Because again, nature knows of no such distinction when it designs biological vision systems through evolution. So what we want to do is an end-to-end optimization of the optics alongside the post-processing algorithm. The process would start with taking the scene features as the input data and then differentiably rendering the measurement that we would get given the current state of the optic. We would then treat this measurement as an intermediary tensor net calculation rather than the end product, and you could pass it to your learnable algorithm, for example, a UNet or a CNN. The parameters that describe the lens and thus controls the point spread function could be optimized alongside the algorithm by standard gradient descent and by auto differentiation. So in this case, we'd actually expect and want to get blurry measurements that are optically encoded because we have a backend to process them. So the project I'm presenting on is a software that we wrote called D-Flat that enables this optimization. It solves some of the challenges inherent to it and ultimately tries to simplify the procedure. The talk's an overview of what the code itself does and how it basically handles everything that goes into this box that we call rendering. And it ultimately lets you co-design a new type of optical technology called a metasurface. So you may be thinking, what are metasurfaces? You keep saying them. What I'm showing you here are qualitative depictions of metasurfaces, and I'll actually show you in the next slide a real electron microscope image. But metasurfaces are these flat optic lenses, and to a large extent they're pioneered here at Harvard by my advisor Federico Capasso. And they're made by taking a simple glass substrate and patterning millions of nanoscale shapes on the surface. All these shapes are the same height, which is why it's called a flat optic. The interesting thing is that we as the designers have the freedom to decide what type of shapes we want to use, for example, cylinders, rectangles, or some freeform structure, and we can choose how they vary across the surface. So instead of controlling light by changing the thickness of glass like you do with standard lenses, we're going to manipulate light by changing the shape at each location. And the important thing about metasurfaces, which make them exciting, is that they are polarization, depth, and wavelength dependent. So you can create those point spread functions that I mentioned earlier. Now again, these structures are actually too small to see with a light microscope, so you have to use an electron beam microscope, and that's what's shown on the left. For reference, the actual sizes of the shapes we're trying to optimize are smaller than even the textures on the size of most microorganisms. So this picture is a microorganism named a tardigrade. And this ends up being kind of one of the key challenges in optimizing metasurfaces. They could be made on a centimeter or millimeter scale in diameter, but they have to be numerically modeled with this nanometer scale precision, leading to a high computational complexity. So how do we know what a metasurface does after it's made? Given a metasurface as a three-dimensional physical structure, we first want to parameterize it, parameterize the optic as a tensor of shape parameters. For example, if we use nanoscale rectangles, then we would define this tensor as the widths wx and wy at all locations. There's then some optical function that we refer to as optical model, which prescribes how this collection of shapes together would transform an incident field of light. And the piece that we need to know for imaging is the transmission t, which is the amount of light that will go through this lens, and the phase delay, phi. And phi actually directly relates to the angle that you bend a light ray in this like ray picture of optics. So these metasurfaces are really wavelength and polarization dependent, as I mentioned, so we have to define this with respect to some polarization basis like x and y, and with respect to the wavelength of light. And it ends up that the only rigorous optical model that exists for light is Maxwell's equations. And you might remember this from undergraduate physics. They're a set of four differential equations. They're kind of ugly to look at, but they can only ever approximately be solved numerically. There's no analytic solution. And it's quickly intractable to try to solve Maxwell's equations across the entire millimeter scale device with this nanometer resolution. So we have to introduce an approximation. And this approximation is the idea of a meta-atom as a building block. So we break up this device into the smallest unit, which is just a block that holds a single shape, and then we solve Maxwell's equations to get the optical response for just that block. And we could build up a data set by sweeping all instantiations of the shapes. And this is what we do as shown on the right. So for a single wavelength, we can sweep the width along x and y of that nanofin, and you can see how the transmission of phase that's imparted to incident light would change. You can also freeze one of the widths and sweep the wavelength, and each vertical column would show you how wavelength dependent this feature is. So having a pre-computed data set is cool, but it's not yet good enough because for a co-optimization task that's based on gradient descent, we need an auto-differentiable optical model. And there's two options, both of which we've worked on. So the first is to use an auto-differentiable field solver. You would simply code your numerical solver, your Maxwell equation solver, in PyTorch or TensorFlow or JAX. And so when you do the forward calculation for a small piece of the lens, you would automatically get back the gradients of the shape too. This ends up being too expensive for computational imaging, so I won't really talk about it more. The solution that we do use is what's often called neural representations. So first, we take this auto-differential field solver, and we compute this data set. And now we train a multi-layer perceptron, which is basically a vanilla neural network, to learn the optical mapping for a given data set. And it ends up that just a simple MLP with two layers and about 512 neurons each is enough to really accurately reproduce this optical mapping. And what's important is that it does so with a factor of 10 to the 5th to 10 to the 7th fewer floating point operations per evaluation. And so for reference, we also looked at some other simple approximate functions. There are representations called elliptic radial basis function networks. You can also try to fit a multivariate polynomial. And what we find is that for anything like a rectangle or any shape more complicated than that, these other representations fail to really accurately capture the optical model. So we end up using this MLP as our differentiable representation. And now with that information out of the way, I can really start to fill out in more detail what D-flat does to make co-optimization possible. Specifically, the sequence of calculations that have to go into this rendering block. So we start by having or by initializing a metasurface shape tensor. And it's a learnable parameter just like the weights in a neural network block, but here it corresponds to something very physical, right? The actual optic will make. And then we use this pre-trained neural network to solve for the optical response quickly and efficiently. And after, we can compute the point spread function I mentioned before by a process known as field propagation. And lastly, with the point spread function, it ends up being quite trivial to simulate the measurement that you would get on a photosensor because it does represent the impulse response of the actual camera. I briefly want to highlight why we found it convincing to write the software that I'm talking about. And while a lot of time and energy was at first spent thinking about the physics, a lot of time later went into kind of the software architecture side to think about how could we make something that's versatile and actually scalable to more people. And specifically, this method kind of implies that we'll end up having to manage a really large collection of data sets and models. So you can consider that for every shape type, like a rectangle, a cylinder, every choice of the material, the block size, the height, all these things will require generating a new pre-computed data set. And so we quickly accumulate dozens of data sets for different metasurface libraries. And the way we ultimately chose to handle this was by creating code where you can query a data set by name and it's automatically downloaded from a server, so everyone has access to it. And the data sets all have a certain standardized form, so you can speed up its integration into machine learning pipelines and training MLPs that represent them. We also have this auto-differential field solver, which we end up not using much for getting the gradients, but we do use it people can use it to make new data sets and put it in this form. And for every data set we just talked about, you're going to have multiple pre-trained models. And that also poses a challenge because every MLP will ultimately have a different number of input and output dimensions, different architectures like layers, or you might put attention in there. And more importantly, they all have a different set of pre-processing steps that you might need, specifically like normalization terms, this shape constants. And so the way we handle this again is by creating code where the pre-trained models can now be called by name, and then the weights and the configuration files will be downloaded from a server. These models are then assembled on fly according to the configuration file, so you can have any type of architecture. And the model you get has a nice standardized form, so the functionality is the same regardless of what shape you're working with. And I can show you briefly in part what that looks like in practice. So you could load this D-flat Metasurface module, and you can just call your pre-trained network by name, after which it's just download from storage, it's assembled, and you can immediately start to use it in place of your field solver. So you initialize some shapes and the wavelengths, and when you call this off the model, you get back the phase and transmission. You can also do a reverse lookup, meaning if I had the phase and transmission I wanted, I can call a library. This is different than the one I used above, and I can solve for the shapes that would give me that response. Now, the next piece that we need in our optimized framework is field propagation, which means given the phase and transmission on the metasurface that we got from our optical model, we want to compute the points per function by propagating the field forward to the sensor. And before we talk about more, I can just show you what that looks like in practice. Sorry, let's see. So what I'm doing here is I'm moving the sensor backwards, and we're looking at how the field evolves as it moves through space, starting from the metal lens. And the output is obtained by a theory called Fourier optics, and by essentially computing some solution to a double integral. So our package implements these calculations in PyTorch and TensorFlow so that you can use auto differentiation, but there's a little bit more to the story. Specifically, there are quite a few ways that you can numerically solve the propagation equations, and I tried to account for all of them. So there's an approximate solution to the integral called the Fresnel method, which involves a single 2D Fourier transform. And if you had radial symmetry, however, you can speed up the calculation by replacing your Fourier transforms with a Hankel transform. So the Hankel is the radial analog of the Fourier transform. It's not coded or built in any auto differential software that I know of, so I code it by itself. There's also an angular spectrum method in 2D or radial form that we worked out, and it gives you an exact solution, but usually takes twice the number of transforms. So a good code to do field propagation for either method actually has a fair number of hidden steps besides just solving the integral. And these steps range from things like upsampling a field according to a few different conditions. You actually have to zero pad because that determines your output field resolution. And once you do that, you typically resample because you're calculating your field on a smaller grid than the actual pixel size. And in the end, it's also necessary to have as many variations of this calculation as possible because there are scenarios where one method is more accurate or more computationally efficient than the other. And you can easily find scenarios where one is actually completely intractable while the other has scaled very nicely to your data and it works well. So ultimately, this is something that we thought could be standardized because it's an operation used a lot of computational imaging, but as far as we know, there was no package that kind of presented this for researchers. Now I want to pull these pieces together and show you in a demo what it looks like to optimize a metasurface. So we initialize a shape tensor, we use a frozen MLP as our optical model, and then we differentially propagate the fields to get the points per function, and then we can update the shapes just by backprogramming gradients through gradient set. And specifically, this demo tries to optimize the shapes on a metasurface to produce a multi-foci points per function at the sensor. So it's interesting, there exists an analytic solution that's necessary for the phase and transmission profile for each focal lobe alone, but there's no obvious way of how to merge these three behaviors into one lens, and that's where optimization comes in. So if I play this out for you, we actually start with uniform shapes across the lens, and you can see as the optimization runs, it changes and it takes shape to actual kind of this focusing profile. And then I'll run it again, and you can see on the right, the light starts by going straight to the metasurface, but as the shapes start to change, it learns how to focus the three spots. And this is in log scale intensity. Um, so you can see there's actually still light that's being scattered. It's not a perfect lens. Okay, so why does this matter? The goal of this project was to enhance the union of optics and computer vision and to enable devices that we might call task-specific vision systems. An example is the depth sensor, but one more example that we've been looking at is optical computing. And by having the right optics, you can replace, for example, a purely digital image processing operation like edge detection with a cheaper optoelectronic version. In other words, part of your calculation is done by the light for free. So here we wanted a metasurface that would create measurements of our scene with different blurs for different polarization states of light. And we could get a set of these four optically coded images just by using a polarizer mosaic photosensor, which is commercially available. We would then just linearly add or subtract these images with certain weights to get back a differentiated image at the cost of only 7 floating point operations, which is orders of magnitude fewer flops than the equivalent digital operation. Now, it ends up this task is exactly point spread function optimization like I showed you in the last demo, and it can be rigorously formulated as optimizing on point spread functions to be polarization dependent and to code different halves of a Gaussian function on different polarization states. And when you do this, you're actually guaranteed to have a linear combination of images that will correspond to the derivative along any angle. Um, and so this was the first time that optoelectronic processing was done in a single snapshot, and we used D-flat to run this optimization. So to wrap things up, a goal in writing D-flat was to try and make optimization of flat optics as easy as optimizing a deep neural network from a code perspective. And what that means is using a pre-trained metasurface model should be as easy as using any pre-trained clip or like a perceptual loss. And if you're not familiar with those things, those are basically pre-trained neural networks that are used in loss functions for a lot of more advanced machine learning tasks. And the challenge is that each metasurface model that we work with is kind of like a clip trained in a different language, and we'd like to have all of them available. Another challenge is that, or another thing we thought about is that these modules for field propagation and for image rendering should also be as easy as using just like a standard conv2D layer in PyTorch. And the challenge here is when you start to implement them, there's a lot of branches in your code for the different conditions, configurations, these different approximations, and you don't want to lose out efficiency for any one scenario. And so the end result kind of looks something like this, where again, you could import this package, you can import your field propagators, your optical model, and you initialize all the field propagators in the same way. You specify things like the output distance, the output resolution, your pixel size, if you have radial symmetry, refraction engine, and you load your optical model. And you can write the main body of this optimization loop, just like the ones for the demo and for the point spread function engineering project like this. You initialize your shape tensor, which I call Z. You define what wavelengths and what point source locations you're using at that step. You can pass it to a metasurface model to get the optical response. You pass the optical response to the point spread function, and that gives you the sensor intensity. And then you can write a simple loss function like the L1 or L2 loss of your intensity versus your target. And you could call error.backwards just to get the gradients. And now you can start updating. A piece that wasn't discussed much in the talk is image rendering, but it is coded. And once you have the point spread function, it ends up being really straightforward to render. So it's not worth going in much detail. So thank you for attention. And I'll highlight this code package has a lot of some of the features you expect in kind of a standard software as continuous integration and a PyTest workflow. And what that means is that if someone pushes an update that breaks the test, the push is rejected on GitHub. It's got complete dot strings, and it used to have a read the docs, but hasn't been updated. It's on the Python package, meaning you could just pip install it with D-flat. And that's all. I'll leave this up here, but there's a lot of also interesting projects for all skill levels if you're interested. Thank you.